Good morning, everyone. Myself Devika, working as Assistant Professor in the Department of Electrical and Electronics Engineering at Sri Muthukumaran Institute of Technology. Today, we have discussed the topic and subject on MR 3452 Control Systems Engineering for 2021 revisions. Today, we are going to learn the topic root locus. So, introduction. An automated system designed to monitor a target within a visual frame can be conceptually in the following way. These are the block diagram of the servomotor mechanism. A root locus diagram usually represents the location of system zeros and poles plotted on a complex plane, featuring both real and imaginary axes. So poles are denoted as marked as X, zeros are marked as 0. Advantages. So this approach serves as a highly effective visual tool for analyzing how changes in a system parameter influence the positions of the controls closed loop poles. Example 1. The root locus of an open loop transfer function denoted as G of S demonstrates the trajectory of all potential closed loop poles and zeros as system parameters vary. So here the poles and zeros. So f of s equal to k into s minus z1, s minus z2 till s minus z power m divided by s minus p1, s minus p2 till s minus pm. Here z1 and z2 are zeros, p1, p2, pn are poles. So poles are marked as x, zeros are marked as 0. Guidelines for sketching root locus. Step 1. Determine the total count of poles and zeros in the system. Step 2. Remember that the root locus plot is always mirrored symmetrically across the real axis. And step 3. On the real axis, the root locus appears on segments located to the left of all number of poles and zeros combined. Guidelines for sketching root locus. So rule 4. Determine the point where the asymptotes intersect the real axis are denoted as sigma and calculate angles of angular central at which these asymptotes extend. So sigma is equal to sum of open loop poles minus sum of open loop zeros divided by n minus m. N means number of poles, m means number of zeros. Example 1. Illustrate the root locus for the closed loop control system. Here the given diagram. So 1 plus kp g of s h of s equal to 0. Here g of s equal to 0, 16 divided by s into 0.0174 s plus 1. So numerator and denominator. So we know that the numerator is 0, so the denominator is denoted as poles. Example 1. So step 1, convert the closed loop characteristic equation into standard form. So 1 plus 27.58 kp into 1 divided by s into s plus 57.47 is equal to 0. So step 2, determine the open loop zeros denoted as CZ along with the open loop poles represented by P. So no open loop zeros. In a denominator, the constant value is 1. So no poles are no zeros are here. Then open loop poles P1 is equal to 0. I mean S equal to 0, P1 equal to 0. Then S plus 57.47 is equal to 0. So P2 is equal to minus 57.47. So we have no zeros and what two poles P1 and P2. Step 3. Identify the portions of the real axis that should be incorporated into the root locus. So we have to mark the poles P1 and P2. We have choose any test point on the negative real axis. So we write a right side of the plane. We have to check the right side of the plane. We have even number of poles means odd number of poles means the part root locus is available. If even number of poles are available, even number of poles right side of the plane, we have to check right side of the plane. We have even number means the root locus is not available. So in this problem, P1 we have to test point from P1 to P2 from anywhere from P1 to P2 the right side of the plane, we have to check right side of the plane. We have only one pose. So one is odd number. So from the root locus is available from P1 to P2. Then we have to choose the test point on from P2 to infinity. The right, we have to check the right side of the plane. We have two poles. So the even number of poles means the root locus is not available. So we have the root locus not available from P2 to infinity. So available only from P1 to P2. Step 4. Identify the asymptotes and the angle of centroids. So asymptotes, we know that the formula sigma is equal to sum of poles minus sum of 0 divided by n minus n. Centroid is equal to. So then angle of asymptotes, theta is equal to 2q plus 1 into sum of divided by n minus n. N means number of poles, m means number of zeros. We know that number of zeros is equal to 0, number of poles is equal to 2. So 2 minus 0 is equal to 2. So we have k means 0, 1, 2. So here 0, 1, n minus n. So we have 2 minus 0 means 2. So q is equal to 0, 1, 2. So for every q value, we have to find the angle of asymptotes theta. Theta 1, theta 2, theta 3. We have to find. Step 5. Identify the points where the system breaks away and breaks in. So we have to find the breakaway means breakaway from two real poles. For that means we have two real poles means we have to find the breakaway points. Likewise, we have two real zeros means we have to find the breaking points. Here there is no zeros, so we have not find the breaking points. So we have only breakaway points. So we have taken the characteristic equation from the transfer function. Transfer function we have to differentiate with respect to s. So for this characteristic equation, and we have to find the roots of this characteristic equations. So here s is equal to minus 28.74. So and we have to apply we have to apply these roots in these k values. We have to get the answer is real and positive means the breakaway point is the s equal to minus 28.74. Example 2. Introduce a feedback control system designed for precision positioning. So input R of S, controller K into S plus 80, plant G of S equal to 16 divided by S into 0.0174 S plus 1. So output Y of S with control signal U of S. These are the root locus diagram for this transfer functions. Example 3, likewise the same in example 2. So we have to find step 1 and step 2. We have to locate the poles and zeros. Then we have to draw the diagrams. And step 4, we have to find the asymptotes and centroids. And then we have to find the breakaway points. Advantages of root locus. It shows stability clearly and graphical method, and it helps in choosing the correct gain value for desired performance and transit analysis. Disadvantages of root locus: approximate method and time consuming for complex systems, limited to single parameter. It requires practice, difficult for nonlinear systems. Application of root locus: it is used in control system design, stability analysis, PID controller tuning, electrical and mechanical systems, and aerospace systems. These are the reference for further study. Thank you.